good for now. Hello, everybody. Thanks so much for joining us today. Welcome back to the Revolutionizing EEG webinar series hosted by your friends at Wearable Sensing. So for those of you who might be new to this series, we're going to be exploring the many exciting ways in which researchers are using advanced dry EEG systems to bring their research out of the lab and into the real world in order to study the brain in more naturalistic and ecologically valid contexts. And for our second episode today, we're absolutely thrilled to be hosting Dr. Eli Kinney-Lang. Eli is an assistant professor at the University of Calgary, and he's the director of engineering for the BCI for Kids lab at Alberta Children's Hospital. He's been working on translating brain-computer interface technology for children for over a decade, focusing on everything from pushing forward basic neuroscience questions to engineering new BCI applications, and even implementing these solutions in real-world clinical environments. He has a strong interest in user experience aspects of BCIs for children with complex needs, and in particular, how to use accessible game development to make BCIs even more engaging and intuitive to learn and eventually master for these kids. All right, so just a quick reminder for the audience, we're going to have a Q&A session in the last about 15 minutes or so. So please be sure to submit your questions down in the Q&A in the Zoom log so that we can go through them after the presentation. All right, with that said, thanks so much for joining us today, Eli, and I'll hand it over to you.
Sounds great. Thanks. You should be able to see my screen. Yes.
Yes, looks good.
Perfect. So I want to thank you so much, Ryan and Cameron, for putting this on and inviting me to talk a bit about what I do in my day job, as well as some of the stuff that I'm doing from a startup perspective on how to build brain-computer interfaces for kids, in particularly trying to understand how to design applications for them for real world use. So this is one of the kids in the program that I've got to work with for a number of years, who's amazing. And I just want to highlight that none of this work would be possible without them and their families working with us to inspire sort of the next generation of BCIs. Some quick disclosures. You'll see work that I do from BCI Games, and I'm the CEO and founder of that, as well as I'm a member of the BCI Society Board and consult with Brain Care Technologies and possibility neurotech. So, overview for the talk today. I'm going to talk a lot about BCI for kids. Why do we care about brain-computer interfaces for kids in particular? What are the benefits for focusing on pediatrics, as well as what is the BCI for Kids program here in Calgary, Alberta? I'll talk about the high-level idea and mission and a few highlights from this, but then I'm going to transition this talk a little bit into how does BCI intersect with interactive digital media, which is the sort of fun way to say games. I'll talk a bit about the rise of accessibility in game design. You guys get to talk about this growing wave here, which is exciting. About designing games for BCIs, designing applications that are intuitive in that space. And then I'll talk a little bit about the BCI Game Jam series, which is something that I've run for a number of years now. And Wearable Sensing has been a great sponsor for this event. I like to show off sort of what the really cool independent game development community has put together. So there's a lot to cover here, and hopefully we'll get through it in time. But first, for those who maybe aren't familiar with brain-computer interfaces or you've just heard the topic before, I'm going to do a real quick review in 90 seconds or less. Happy to go into details about this later. This is just a high level for you to be able to understand the things that I say. So the goal of BCIs, I'm sure lots of people know this, but it's directly use brain activity to drive some user-desired action or outcome, and that's typically on a computer. So if you have something like an acquisition system, an EEG system, the wearable sensing system, you are picking up brain signals from the surface of the scalp, and those specific actions then need to be processed. You do a little bit of signal processing here to be able to decipher what the intent is from the noise. And that signal processing eventually leads to feature identification. So you could think about a feature as opening or closing your right hand, or imagining opening and closing a hand. There's many ways for this feature identification to come through, but it's really the goal of trying to separate the intent of what you're doing from background noise. Once you have those features identified, you want to extract them and classify them. and you put them into these different output classes. So you can decide, okay, that was right hand versus left hand versus maybe tongue, or sometimes in a lot of the work that we do just an active action. It might be right hand and left hand simultaneously versus being at rest, or it might be some stimulus on the screen, as you'll see. Once you have those output classes, you then feed that back to the user, and that completes the whole BCI loop there. So what are we doing for BCI for kids in particular? Now that you have a feeling for what that is, how are we building the next generation of this? I really want to emphasize that children are severely underserved in the BCI community as is. This is a figure I made a couple of years ago, which is looking at the number of publications in PubMed on brain-computer interface in general versus those with children. So in orange here, you can see that's all of the BCI publications steadily growing over the years, and this is a little bit outdated. And then down in the blue there at the very bottom, those are the publications with children only. So you can see it's still quite a small amount. It's looking at how to translate this for kids. And this is actually a really good moral imperative to advance these for children with neurological disabilities because they have a lot of advantages and are going to be lifelong users. So really, we're trying to get people to think about BCI and rethink what's possible with them. Because again, this population is an ideal population for long-term use. They're going to use this assistive technology for the rest of their life. This little boy here is learning how to use a BCI system to actually move his power wheelchair. And here he's practicing turning it so that he can hit these Star Wars balloons, which was a lot of fun. And kids like my friend here are capable of significant changes in their brain. So the things that we're helping them learn right now is key to them being able to use these systems later on as they get older. And really, the important goal here is that improvements for children actually helps all BCI users. So if we make it functionally work for kids, then that can translate really well up to adults. Going the other way is not necessarily guaranteed. I can talk about that more, but really diving into it, what are some of the advancements here in BCI that we're seeing that could really benefit all users and not just children? Oftentimes, some of the challenges that we talk about is difficulty in recording data with kids, especially younger kids. You get a lot more movement, you have noise, you have problems with headrests affecting the data. But the benefit from trying to tackle these challenges and getting it to work with very young kids is that we get improved signal processing approaches. We get better headset designs, we get artifact removal working better, we get to learn how to do proper channel selection on the fly for places that typically you might not think about. Similarly, there's a lot of variability in development. Two 6-year-olds might be developing at different rates, and a kid who has an early life injury or disease that might change their developmental trajectory, that means that they are going to be in an even more different place than another child. And what that means is we can promote greater BCI generalization. Similarly, tasks are quite complex, and it takes a lot of effort to look at how to teach these tasks to adults. And what we can do is try and break those down for kids. So we can design more intuitive BCI tasks. That's really going to be the focus of my talk for the rest of the day. And key here is most BCI applications are actually built for adults, and then we just hope that they'll work for kids. But by focusing on kids, we can focus more on play and enjoyment, which scales very well up to adults, because adults also want to have these tasks be enjoyable and not just an arrow pointing to the right and an arrow pointing to the left with no meaningful feedback. So taken all together, I think there's a real need for including children in the conversation of BCI. And that's what we try to do in the BCI for Kids program in Alberta. So our aim is to give children with severe neurological disabilities and their family access to the wide variety of BCI technology as a new means to participate in life and do a bunch of different things. I'm only going to highlight a few things here. As I said, I'm going to focus a bit more on the play and leisure bit and the way that we make this engaging and intuitive. So some highlights from BCI for Kids, as Ryan mentioned, we do a lot of different things, but I'm going to talk a little bit about just two things today. A project focused on sport participation and another aim to bring play and leisure to life. If anyone's interested in some of the other work that we do, such as neurorehabilitation work or power mobility work, happy to answer questions on that at the end as well. So sport participation for children in particular using a BCI system is one of the big efforts that we've been putting forward over the past number of years. And this work is led by Dr. Daniel Comadero Marquez, who's really trying to look at how we can bring BCIs into the Paralympic space for the game boccia. So he's been working on developing a brain-computer interface controlled boccia ramp so that kids can play sports and participate in sports for the first time. So the objective here is to develop and validate a BCI-enabled boccia ramp so that children with severe motor disabilities could play boccia with minimal assistance. For those who may not be aware of what boccia is, it's a game that is focused on precision and is really a high-level Paralympic sport that is trying to take a target and throw a couple of balls as close as possible to that target. And this has a really great adapted form for individuals who have very complex disabilities at the top end of the sport as well. So here you can see a picture of a number of these individuals playing with an assistive ramp and an assistant who will actually turn that ramp for them to be able to target and throw their balls in a specific space. However, this still requires, in the most adapted form, a constant communication with the assistant, still requires a number of things that some of our kids who may be non-speaking actually are not able to do. And so what we're trying to do is bring a robotic ramp and BCI to give as much independence at that play level as possible. So the goal here is take a system like wearable sensing, process the brain data, send that to a robotic ramp, including how to move the ramp, how to target with it, and when to drop the ball, and give that feedback to the player so they can practice this sort of on repeat and get better at learning how to play this sport and play with friends at some point. This is an example of our version 1 software. We were at a conference. You can see Dan there set up with robotic ramp here on the side. And you'll see it's starting. There's some flashing here. And this individual is attending to this drop flash, trying to get it to drop on the ramp. You can see he's very excited when he actually gets it to go. And so this has been working very well. We got to go through. And when we took this to patient partners, we had based this on assistive technology that uses a two-step switch scanning approach for selecting objects. So you select rotate and then you'd select left and right. They gave us some really great feedback on how we could maybe encode this simultaneously. So following some patient engagement work done by Daniela Bork as well as Dan, we are able to update our software to make this a bit more intuitive to use and actually use the brain signals a bit more effectively coming out of the P300. So you can see already we've updated it to be a digital twin where we have this boccia ramp that is placed in a one-to-one sizing with what it would actually look like in a court itself. And you have now this fan shape that is encoding both position and height of the ball. So it'll rotate and lift the ball to the specific height that you want. And we're able to build out a number of applications. So we're advancing this still, and we're working on now the iteration 3, where we'll bring this as a multiplayer game for players and kids to practice at home. So that's one dimension of play. But one of the other big dimensions of play and leisure has been art for our kids. So this started a number of years ago where we would hook up a Sphero robot and roll it around in paint to create some unique art pieces. And our kids have really loved this as an expression of themselves. This young boy in the middle, John, he actually created his own Instagram page, sort of building up this art. And you can see that a number of our kids have entered in a couple of art competitions, and they've really enjoyed that side of engaging with expression through a BCI. Similarly, for young kids, one of the first things that we do is introduce them to toys and getting them to work on a couple of cause and effect toys. This young girl on the left here is turning on this bubble tube, again, trying to do this imagined action versus rest state. And on the right-hand side, we've hooked up a little tiny car to the BCI to knock over these blocks for this young boy. And the final thing that really is going to drive into the things I'm quite interested in is gaming. So this is the number one thing that most of the kids who come into the program really want to do. They want to play games with their siblings. They want to play with their friends. They want to play with their families. It's been quite a long time now. This is from early days of the BCI, but this young boy, Nick, he's actually sitting here and playing a game for the first time while his brothers are watching him play. So it's this sort of inverse of what he had experienced most of his life. And so in this case, Nick is responsible for the jumps, while Ziana here is moving the character left and right. And the question became, well, what can we do with gaming, and how can we build it up so that the BCI system is integrated from the ground up? And the question that I get sometimes is, why are you focusing on games? That BCI systems should really focus on communication or power mobility, which are amazing and critical goals for BCIs. However, the focus on games is really important, I argue. And why do I care about this? Well, if you take a look at things like Pac-Man, Pac-Man is something that is instantly recognizable, and people think about how they could adapt Pac-Man to be playable by individuals in a wide variety of settings. Especially recently, there's been a big push, as you'll see, about accessibility in game design. And with Pac-Man, it's already pretty high contrast. You can tell sort of which characters are which. It can be adapted for low vision gamers quite effectively. And people sometimes don't think about the actual input scheme for Pac-Man. Because what happens when you can't control this character left and right with precision is that the game falls apart from the top down. Because it was built for able-bodied inputs to move Pac-Man around at a speed to avoid the ghosts, to collect certain things. And as soon as you lose that input capability, the whole game becomes unplayable. And there's actually thousands of individuals who may not have a reliable way to interact with games like this that are built for able-bodied controls, but now are reliant on a BCI system to try and play them. And my interest is, how do we change that? And how do we use that to help teach some of these skills that are useful for things like power mobility and communication? And I'll say here that accessible design matters quite a bit, and it's a game changer. So this is a really good article about the unpredictable challenges of gaming with cerebral palsy by Jane Human. And I'm going to just take a few quotes from it. But she's talking about how, for her, imagine for a moment having a brain that processes stimuli more slowly. So picturing a 5-second delay between deciding you want to do something and then actually being able to do it. And that is a huge problem when it comes to these sort of quick movements and moments in gaming. And so, depending on the nature of the game, this might be fairly a straightforward task, or for this individual, it might turn out to range from complicated to borderline impossible. And this you can think of as a really common experience for individuals with cerebral palsy, or those who might be using a BCI system where there is a delay happening and an inconsistency there. And what she mentions is that in this game pictured, Fallout 4, they have this feature called the VATS, which slows down time. And she says that Bethesda may not have intended that as an accessibility feature, but because it was included, it really let her have fun for the first time in her life in a game that involved aiming and shooting, because it helps slow everything down so that she could actually play this game. And she goes on to suggest that she would love to encourage developers to consider accessibility from the ground up when designing their games. Things like physical impairments and cognitive impairments, sensory impairments that might be impacted by gameplay mechanisms and ways to teach that. And goes on to emphasize the sort of patient and partner engagement that I think is critical in recruiting disabled players to test the games and ask them what they think of these mechanics. By doing so, the developers can play a role in making the game more enjoyable for everyone. And that goes back to the sort of argument that I have of making this function and fun for kids, makes it enjoyable for everybody, adults included. So I'm going to talk a little bit about this trend in accessibility in gaming, and talk about a few examples that have come out in the past couple of years of these big name sort of games that have included accessibility as a core feature in them. So this is The Last of Us Part 2, and it's really a watershed moment, I would argue, in pushing accessible game design forward. They included hearing support, visual support, and motor support for all players that can be turned on and off. In the motor support, they changed the ability to do different puzzles and interact with them, that you could either hold buttons down or press them once or have help solving those puzzles. In the visual space, this is a screenshot from the game itself where Ellie is looking, and there's a couple of enemy characters that you can see right there. versus in the standard mode versus the low vision support, you instantly can see how supportive it is in being able to track who is your friend, where you're at on the screen, and potential enemies here in red. And there's a really great conversation that Steve Saylor gives about this and this moment of him being able to play this game from the start as a blind gamer and the importance of including this early on. More recently, Prince of Persia: The Lost Crown has really been a modern masterpiece on accessibility as default within it. I have some screenshots here showing all the different ways that they again included hearing, visual, cognitive, and motor supports. This is showing the main character dashing over these spikes that would cause your character to get hurt. But in the accessible vision space, not only do they highlight spikes, but you can highlight each thing independently within the game itself. So if you have the ability to see parts of things without other parts, you can turn on and off that visual support as needed. You can also turn off damage when falling into these sorts of traps. And the big thing that they sort of put forward as a cognitive support was this thing called a memory shard, which created this ability for you to actually not have to remember each part of the map. So this accessibility feature as a memory shard was born from the idea that you run into something like a treasure chest that you might not be able to get to just yet. And rather than just having you mark where it is, you can create a snapshot or create a memory that you can go back and see. And anytime you want, you can pull up exactly on the map where that was and what was there specifically. And the reception of this was amazing. So this was an accessibility feature that they thought for cognitive support. And you can see a whole bunch of people in the gaming space talked about how this memory shard mechanic was a game changer, that it's a genre innovation in this well-saturated genre of gaming here. It adds the best new feature to this type of game, this Metroidvania, in years. They talk about this brilliant feature that eliminates pointless backtracking. And so even though it was built as an accessibility feature, the reception for able-bodied gamers was phenomenal. And this just goes back to the concept that I want to hopefully get across here, which is thinking about accessibility really fosters new design thinking and allows us to find these core features that will benefit everyone. And that I think holds true for building these sorts of games and applications for children. And there's many more games that are building like this from the get-go and are starting to build this up. This is actually a number of games that are using eye tracking built into the game. So they can use the Tobii eye tracking system to be able to control different parts of the game with eye tracking specifically. So we thought about a little bit of accessibility in game design, gone through a tour of why that matters right now, why there's this big moment and movement happening, but what has been done with BCIs and gaming right now? Well, there's a lot of work overlaying BCIs onto existing games. Like I mentioned with Pac-Man, sometimes people try and overlay a control system onto Pac-Man to move around. This is a representation of a group that added BCIs on top of World of Warcraft so that people could cast certain spells within World of Warcraft. Other groups recreate the classics like Pong, albeit I will argue poorly, because they have movement here that is a little bit more challenging than you would do with an able-bodied control system. So they aren't thinking about the game design, they just try and plop it on top and recreate the classics with that. But a lot of these are built in the labs for research, and that's as far as they ever see. They build a small game, they say, oh, that was fun, and then they close the research study and nobody ever gets to play it again. And I think they're thinking a little bit too little about good game design with these new inputs, much like how taking some of the accessibility designs in existing assistive tech and just trying to put that with BCI systems might not be the right approach, as we tried with Boccia. So where do we start? What do we do to make the most out of BCI systems? If we think, okay, we don't want to just plop it on top, we want to think about how to design these games from the ground up to be accessible. What do we do here? And the number one thing you can do, I think, is understand what a BCI can and cannot do effectively when it comes to controlling an application. So really getting that intuitive understanding of what it's like to use a BCI and working with individuals who use these often is the key goal here. So I'll talk a lot about BCI control schemes, and for those who might not be familiar, I tend to break them down into discrete control, and this is things that tend to have like an external stimulus, something that you need to select a single object on the screen. And sometimes this is like the P300 selection scheme or the steady state visual evoked potential scheme, both of those being visual flashes that sort of rely on different internal mechanisms to select stuff with. The pros of a discrete control system is actually quite simple to imagine how to put discrete control into an application and how to implement it. These tend to be really reliable signals that are easy to train and use, so most people can train up on them, and you get immediate feedback on your selection. You either got it right or you didn't. Downside of this is you end up with limited object selection options. So you can only put so many options on the screen, and then you start to bump up against those sort of considerations about cognitive accessibility. It requires setup time and set response times usually. So you might flash something for a couple of seconds and then provide an output. And so that set response time leads to an on-off rhythm in gameplay that's required. And because, again, the two that I'm emphasizing here, it's not just these two, are visual based, you might run into visual fatigue and disrupting things for individuals in that space. On the other side, you have things like continuous control. So this is like your motor, imagined motor movements, your motor imagery, attention-based schema, sometimes mental command schema. And the benefit of continuous control is it might seem more similar in design to a joystick or a button in concept. And you can create both positive and negative actions from that sort of button press. So you fill up a bar if you are doing action one, or you fill up another bar if you're doing action two, or you fill up a third bar if you're doing neither of those. This also allows an asynchronous selection, so you don't need to have this rhythm in the gameplay. The downsides, though, are that these tend to be more unreliable signals. So that motor imagery signal is much harder to pick out because it's asynchronous than something like a P300 or steady state visual evoked potential signal. There's also a delayed response often with these. So going back to what Jane had mentioned in her article, there might be a delayed response that doesn't feel good to use. You start to limit the degrees of freedom as well. So you might have left and right as 2 degrees of freedom, but that's quite hard to understand and implement in potentially depending on your design. And then finally, you might have a lot of right and wrong answers in a row. And how do you handle that? How do you handle this sort of continuous stream coming in? So what does this look like for discrete control in some game examples? Well, what can it do well? If you think about Pokemon, Pokemon is a great example of discrete control as a menu. So the entirety of Pokemon is menu selection that you choose which Pokemon you want to use, you choose whether you're going to fight or run or use an item, and then you choose the skills that they have. Each of those are discrete selections. Similarly, Slay the Spire, if people are aware of it, card game based things where you have a select number of options here. Those are great examples of discrete control going well. Classic example of good discrete control is chess. You have a limited number of options that you have on the board at once, where you max out based on the uh, number of components that you have, number of pawns or rooks, etc. Pieces is the word there, and what they can do. And once you select one, how do you go back or select where it should go? What can it not do well? Well, things that require consistent, precise movement can be quite challenging. So in this game, this is a Mario Party game. Even though it looks like you have 4 quadrants that you might want to send your person into, what do they do once they get into that quadrant, and how do they do precise movements around is where discrete control starts to fall apart quickly to be able to do that well in a quick fashion. On the other side, what does continuous control do well? You can think about things like Mario Kart or Forza Horizon 5 here. Both of them give the opportunity for you to auto drive on a lap. So they push the gas pedal forward. They say on a line, this is a great accessibility feature. And now you have continuous control just for moving left or right within that space. So racing games like this do a really good job of giving you a limited degree of freedom left and right, but really being meaningful in what those decisions make. Similarly, idle games, things where there's no downside for clicking or clicking more, can be a really good design space for continuous control, where you can click and get good feedback to increase things there. What can they not do well, despite many children asking if they can play Fortnite with a BCI system? Precise aiming and things like Fortnite, it cannot be done super well. And even games like Mario, where there's a whole another conversation I'd love to have with anyone who wants to talk about it, the design of Mario's jumps and the precision of that is really key to the game playing well and feeling good to play. And continuous control can't do that precision super well just yet. But it's really emphasizing here that this is the Wild West of development again. That aim of trying to think about accessibility to create new exciting moments in games and game design and gameplay, that's where we're at. So we're back at the stage of thinking about Pong or Joust or Space Invaders, these classic games that really tried to push what's going on in their systems for new ways and new directions that have lasted the test of times. There's a lot of fun things that we can do in the game design space. I'm encouraging anyone who's talking about this, think about how small changes in your gameplay could actually expand play to anybody. This is again a Mario Party example where you have to jump over these rolling um, obstacles. And if you just slow that down right before they hit the players, you now can expand this to a wide variety of input options. You can make this BCI accessible now by slowing it down so that precision window doesn't have to be quite as tight. And ultimately, that's what I'm trying to do at BCI Games, is try to design for developers and then build for everybody. So we're trying to build out tools to think about game design and game development from an accessibility point of view. And we host things like the BCI Game Jam and have made all of our tools accessible. So these are open source tools if anybody wants to build them. We have a thing called BCI Essentials that we use to build out all of our games. And our goal is to create new experiences that revolutionize gaming for everybody. And so we try and build out fun games and accessible, intuitive games for people. And this is again motivated by the kids. They're the ones who say that the thing they want to do the most is play games. BCIs can enable them to play games for the first time individually. It can enable them to play with their friends in new ways, and it gives them a new dimension of immersion through this. And really, we want to support as many games to become BCI ready as possible. To bring this back to sort of the other work that we're doing, we can actually look at and are currently looking at how we can use transferable skills and teach those skills through BCI gaming at home. This is a game that we've developed for a different study, for an imaging study called Neurami, and we actually took it to a gaming convention here in Edmonton, up in Edmonton, and you can see a young kid using the DSI system there and their parent using a DSI system here, both playing this game next to each other at the convention. And in this case, they're trying to focus on imagined movement to be able to throw a little object and capture these characters in a Pokemon-like fashion that has been built from the ground up for BCI specifically. And our goal is to aid you in the development and design of BCI games. So as I mentioned, we have a BCI Essentials package through BCI Games. We build it out through both BCI for Kids, where we help validate and build new applications, and then we release it as an open source tool. This has a backend that is using Python right now, but we're exploring how to bring this to smaller and smaller devices as an ongoing research project. And we build out these games right now in the Unity game engine and are happy to talk to developers or researchers on how to create bold new games for BCIs. In the past, we've offered support in building games for P300 or steady state visual evoked potentials and motor imagery or other inputs. If you're just interested in design questions, happy to talk about that with you as well. Again, this is all open source. I say it's a startup. It's really mainly just me doing fun things that I think are fun, but happy to talk with anybody. That leads us to sort of the end part of this game, which is the BCI Game Jam series. So this is what we've really been building these tools for each year. And for those who don't know what a game jam is, well, a game jam is kind of like a hackathon where you are building out something in a short amount of time, specifically a game. And we give a lot of options and opportunities for people to be unique and creative in their designs. And the Game Jam series has been supported by Wearable Sensing and other companies for a number of years. And we really want to thank the companies for their support. So without it, we couldn't bring developers in and give them some pretty exciting prizes through this competition. We ran 4 of them over the years, so 2019, 2021, 2022, and 2026. And we've had hybrid participation. So people can participate locally in a couple of sister sites that we've run in Calgary, Edmonton, sometimes in LA. We had some at UBC last year in Italy, as well as just people from around the globe participating on their own. We've had about 50 games developed through this, and all of the developers of these games keep their IP. So the only thing we ask is that we can share it with kids in different hospitals or places to be able to get them to play these games and give feedback. This last year, we actually had 20 new games built, and they're to be played by children here, as well as I'm going out to Ontario in a couple of weeks to play these games in a sort of game jam night with Kids Ability in Ontario, which I'm very excited about. So I'm just going to highlight a few of these games. If anybody's interested in the other ones and the design approaches, I'm happy to talk through. These are just some fun ones that I wanted to emphasize throughout the years. So this was from our very first game jam, and this was a game called Kirby Pop. No relation if you're from Nintendo. Please do not sue us. And really, this is like Angry Birds, but with a little Kirby character trying to eat a cake here. And this young boy is selecting between sort of moving the character up, down, left, or right. And if he clicks the center there, then he will send Kirby off. This game was built in 2019 and it has gotten played by so many people across Canada and throughout the world. This is work by the Pearl Lab called Sumo Boodle. And you have these little characters that are trying to smash into each other to knock them out of a ring. So you can see here, you have this timing aspect to try and focus on when you're aiming towards the opponent and knock out the other character. We've had kids play this together with their able-bodied siblings, with their friends, with us as the researchers, and it's been a really fun game for them to play through. I like to show this game because sometimes I talk to people who say, I don't know how to do game design. I'm not sure if I can make anything worthwhile. This was an endless runner game submitted by a guy named Matthias, and essentially he asked me what I would build, and I said I'd build an endless runner where you'd have a small zone to try and jump over an obstacle that slowed time down. And so he put this together and he felt a little bit bad. He said the graphics are really simple. And I'm just going to hit play here. And it's two states of this stick figure running back and forth. What I was able to tell him, though, is one of the kids who came into the program saw this game and loved it so much that they played for 2 hours straight. They kept laughing at the little stick man running, and they loved how the simplicity of the game let them just enjoy the stick man running, trying to jump over things. So even if you aren't experienced in game development, game design, it doesn't have to be super polished. For many of these kids, the key thing is they get to play for the first time, and they loved this game. Some games from the 2021 Jam that I'll highlight. This was a group out in Montreal, the Musea Lab, and they put together a visual-based board game, essentially. So you can see here, you have two characters. This is a multiplayer game where they have to move through and select where on the board they want to move, and then it automatically moved an opponent to other spaces. And our kids really loved the dragon and the board game theme and being able to play with siblings and families. From that same competition, we had a sport game submitted, curl, which was really exciting because you took turns doing curling. It's very Canadian as a submission, and the kids loved that. It was a sport theme. They got to play with their friends and family or against the computer opponent. And I like to show off curl because I contacted the developer. She's actually a software engineer for me now, which is great. But years ago, we worked together and took this from this game prototype that you see here, where you took turns sort of doing things such as brushing or sweeping, and have released it after the jam as a fully accessible game for BCIs on Steam. And so it was designed from the ground up. And I like to show this because I cut the trailer for it, despite her doing all of the hard work. I'm like, yes, I cut this trailer, which was a lot of fun. You can see just how much it grew in its sort of style and design from that same concept originally. In 2022, a few more highlights here. This was the overall winner. I like to show this because, again, it had that sort of cooperative play, but in this case, it was a asynchronous design here, where you would have one person controlling the character, moving left and right, and the other one is focusing on the stimulus here to remove or add obstacles back in. So this is called Brain Buddy. So they got the strawberry, and then the partner looks at this, and then that removes the obstacle for now the caretaker or the family member to move the characters left and right. And you have a couple of these levels where the BCI player basically is responsible for getting rid of obstacles and adding things back in an asynchronous gameplay design. Most recently, some of the really fun games I want to highlight that came out. We have lots of them. I had to choose a few for time reasons, and I know I'm close, so I'm going to wrap this up. This was Bumper Bergs by a team here. They built this in the Godot engine, and you play as the iceberg, sort of driving around trying to knock ships out. The really clever design perspective here that I love to highlight is that you're actually changing the flow of the water with these SSVP flashing stimuli. So you're not controlling the iceberg directly, but rather the rate of flow of the water to move the iceberg around, which again is a really unique way to take that discrete control and translate it now to make it feel more continuous. This was a group that made a game called Blob Bop, which is excellent. Team Mind Control. Hopefully, I have sound on here because the game is absolutely requires the sound. This is a P300 based game, and what you do is you select from several blob opera characters to be able to get them to sing. Might be hard to hear, but each of them are singing different notes, and so you get them set up, and they create then a song together, which is quite fun. And very, very silly, fun animation from this group. And then finally, this is actually my daughter wearing one of the DSi headset caps for a game that was called Ditto Rush at the time. And I'm trying to emphasize that these same control schemes that she's practicing here would be able to help her with computer navigation and power mobility things. So again, these are going to be flashing lights, but it's with a snake-like design there. So this is my 5-year-old has this headset on, and she's focused on these flashing lights to then move right, up, left, or down. And when I talk to the developers here, I ask them basically, as soon as you select one, have the character keep going that way until they select another one. And so my daughter is happily doing this to try and collect all these different Pokemon, sort of focusing on this visually. So that's the end of the talk there. I want to make sure I highlight that the team here is a really transdisciplinary team. So we have a lot of amazing projects ongoing by a whole bunch of students and staff that I don't have time to go through, but really just want to emphasize that there's a wide group of people working in things from neuro and that basic neuro side to biomedical engineering to clinical engineering. We have industry collaborators who help make this run. I really just want to thank everyone for their hard work on these projects. I'm not doing this alone. I have this amazing transdisciplinary team getting these games to run and making these applications possible for kids. These are the sponsors from the BCI Game Jam 2026. Again, thank you, Wearable Sensing, for helping out with that, as well as our partners in BCI for Kids, Endless Era Gaming, the Calgary Game Development Association, and Kids Ability. These are sponsors from the past years, 2022, 2021 examples. And for the day job side, for my work at the University of Calgary, big thank you to all of my funding sponsors. You can see them on here who help make all this possible for these kids. Finally, I want to take the time to acknowledge and thank the children, parents, and families who continue to give their time, energy, and input to make everything we do possible and worthwhile. I want to thank Wearable Sensing for inviting me to talk to you all today on this webinar, as well as the organizers, the Game Jam 2026, our Research for Families group, and the partners there who've helped connect individuals and bring that patient engagement forward, and the whole BCI for Kids team, among others. Thanks. Happy to take questions.
All right, awesome. That was amazing. Thank you so much, Eli, for sharing this really incredible work. These efforts they're really so inspiring. So it's just amazing to see, how many of these kids are able to use these accessible games and enjoy and connect with others. So on that note, we've got lots of questions here in the chat, but just to start us off, it's really cool to see the kids playing these games and enjoying them. But I'm just curious, what is it like from the experience of their families? I imagine as a parent of one of these kids, it's just so cool to see your kid enjoying and sharing and playing with others.
Yeah, absolutely. We get a lot of really positive feedback from the parents as well. And we work obviously very closely with them with what the kids want to do and their goals and their aims. And so I don't have the quotes on hand. We've gotten wonderful feedback from the parents and in particular, again, from the kids and their siblings, when they get to play these things together. We have a this year is our second year of bringing a initiative called Club BCI together, run by Alicia Hilderly, and many others in the lab, where we actually try and create a summer camp for these kids to come and play together and do activities together. And gaming is one of the big ones. And last year, in the first time that we piloted this summer camp, this Club BCI concept, um, one of the older kids, Nick, who you saw playing games with his brother, was teaching the other kids how to play Mario Kart. He was so excited to get them to play Mario Kart with him. And so it was this really sweet moment of seeing him being able to teach and pass on that knowledge and really share in that excitement of gaming with his friends in that club.
Awesome. That's so cool. Yeah, thanks so much for sharing. Great. Yeah, we've got a lot of questions, a couple little more technical questions.
Sure.
So somebody had asked, what kind of BCI paradigms do you use in particular? Things like, are you using things like SSVEP or motor imagery? And then they also ask, do the kids use it in uncontrolled settings, or I'm sorry, in controlled settings, or do they also use it in uncontrolled settings, like at home as well?
Yeah, it's a great question. So, if you could tell, we use things all over the board there. So, we do SSVP and P300 as well as motor imagery and very simplified motor imagery, which is more like switch selection. So, rather than thinking right hand specifically, we just try and take a snapshot at rest and then a snapshot of them attempting some action to be able to select things. So, the paradigm that we use depends greatly on the goal that they are doing and the research project or the clinical session. How often do they use these in uncontrolled settings? We have an ongoing study right now actually looking at BCIs at home and the independent use of that. And so, again, trying to translate this to this sort of unsupervised setting is a big step here. We got a little bit of that during COVID, where we just tried it out and saw what could happen. We saw some success. So now we've really started to dial that in to an actual study and implementation science question of what are the barriers of using these at home? What are the barriers for the families? What are the barriers for the kids? And trying to focus on that. From my own side, I have a study growing out of this most recent game jam about teaching those skills at home, hopefully in an unsupervised setting space. So taking some of these headsets like the DSi one you see there and taking them to the families, help teaching them how to set them up, and then seeing if we can learn some skills at home. So I'll be supervising it to start with, but the goal is to move it to that unsupervised independent use by individuals.
Awesome. Really cool. Yeah, looking forward to seeing more about that. Yeah, there's another question, kind of similar in nature here from Super Z, and they had asked, which BCI application typically do you find has better accuracy? For example, P300 or SSVEP. And then they kind of also asked, in terms of how many sessions do you actually need to run to get this kind of meaningful translation from these different applications?
Yeah, it's a great question. So it depends on the kid is where I'll say, because again, every person is pretty unique. And especially kids who have different developmental trajectories and different abilities, there's different control schemes that will work better for each kid specifically. One of the sort of comorbidities that happens with cerebral palsy or other kids that we see might be cortical visual impairments. So they might actually have some impairment in the visual system. So things like motor imagery can work better at times than a visual-based one like P300 or SSVEP. And we're still trying to work out how to bring the most of these to the most kids. So we just had a master's student, Emily Schrag, graduate from our group, and her whole focus was how do we make the visual evoked potentials, that SSVEP system, more comfortable for kids to use. So it's a very basic neuroscience question there to try and make it less visually fatiguing for our kids, and in particular for kids who might have visual sensitivities. We have another student working, Adam Luoma, working on auditory BCI systems. So for the kids who have CVIs and these systems might not work well for them, can we use audio cues and auditory system control schemes to actually give another dimension of control for the kids? So what works best? What do we see the best on? Depends on any given kid. I will even say for myself, I know I am terrible at SSVEP. which many people think is easy. I work a lot better with the P300 side. I've actually had to have my data thrown out before because of how bad I am at SSVEP specifically. So I can't really answer what is best, but rather that we try and match it to each kid as best as possible.
Awesome. Yeah, that makes a lot of sense. Great. Yeah. Kind of building on that as well, that the next question somebody had asked was, how do these, have you looked at using multimodal signals for these BCI applications? And how do you feel that they fit the scheme of supporting children with different types of disabilities?
Yeah, I love that question because absolutely multimodal signals should be used. So we are just in the nascence, I would say, of trying to use multimodal signals better. But from my perspective, to be honest, and I know we're an EEG seminar, so this might be blasphemous, any output and any signal you could use is a good signal there. So if these kids are able to run it through micro EMG or EMG, I'm actually okay with that. I think that's great. Being able to sense those small EMG movements on the scalp, that's okay by me. I'm actually fine with that. If we can include that with EEG, that's amazing. Work that is hopefully going to be published soon. We have submitted it for review. Has been on using eye tracking, and in specifically the gaze of the individual to be able to start and stop a system so that if you're doing a visual based P300, looking off screen would pause it, and then looking back on screen would resume it. So using things like eye tracking to make sure that attention is being held on the screen, if it's a visual based system, is a good example of where we're thinking and where our head's at with multimodal systems and multimodal inputs. I'm happy with any of them though. So heavy agree, we should continue down this path.
Awesome. Yeah, sounds great. It makes sense. We've got another question here from Shobi. They mentioned that they're building a neurorehab video analysis platform. They'd love to hear your thoughts, and their specific question is, how much, rehab-focused data would you, suggest in order to have the particular game parameters that you need for improvement with these systems?
Yeah, I do not know is the real question or the real answer there of how much data you might need. Happy to talk about that offline and sort of our experience. Most of our rehab focus has been on children with hemiplegic cerebral palsy. So the majority of the kids you saw have quadriplegic cerebral palsy. So it's affecting all four limbs and they may be non-speaking. Our rehab has focused on kids who have hemiplegic cerebral palsy, so a weakness maybe on one side of the body or an affected side, and using things like functional electrical stim paired with BCIs to drive rehabilitation. And so we built out a fun social media application there. We just got this paper published actually recently. If you look up Anna Bourgeois, or myself, it was published this year about pairing social media to this BCI FES rehabilitation. This was a pilot study, so this was really done again in partnership with kids who've gone through these sorts of rehabs. And Anna Bourgeois did a great job including those patient partners in the design consideration and aspect to make sure that what we were building are things they would want to use. So how much you need to build the application, I don't know, but I'd recommend going and talking to those people who you're building this with. Talk to your patient population, get some champions on your team to help design and build that out.
Great. Awesome. Thanks, Eli. Another question here, it's maybe a little bit more technical as well, is how do you currently handle kind of accurately synchronizing different stimuli within the EEG data from all the different stimuli on the screen?
Yeah, that is a brutal task sometimes. So oftentimes we do end up using lab streaming layer right now as our synchronous approach to synchronize the headset and the actual computer application itself. So we pass things through lab streaming layer from the headset to a single dedicated computer, and then within the computer, we send it back and forth from a backend Python processing of all this work, which is taking in that EEG signal, and the front end Unity sending out signals through lab streaming layer to that Python backend. It doesn't have to be on the same computer. We could pass it through a different schema there. And recently, we've been working really hard on trying to miniaturize this and look at other network protocols so that we don't have to rely on lab streaming layer for connection. I've looked at things like Open Sound Control, OSC, looked a little bit at TimeFlux as another synchronization platform. There's a number of these out there that you could look at. I have partners who I work with closely who use BrainFlow quite a bit. So it kind of depends on your application. For us, lab streaming layer is the devil I know. So that's what I've been focusing on.
Got it. That makes sense. Yeah, super insightful. Thank you. Um, well, we've got a couple more questions. I think maybe one to sort of send us off. We're almost here at time. One of the challenges that people often encounter with these non-invasive BCI systems has kind of been limiting degrees of freedom of control for output in the game. So I'm curious, with all these improved algorithms and neurotech applications that we've seen developing, a little bit of an open-ended question, but I'm curious, where do you see these systems going with all these improvements we've been seeing and maybe the next, 5 or 10 years or even beyond?
Yeah, it's a good question. So that's where again some of my passion and my focus is how do we make these more intuitive to use? And how do we understand the difference between able-bodied inputs, like the responsiveness of a button being pressed and the instantaneousness of that, compared to a brain signal. So even though sometimes there's an analog saying, oh yes, or an analogy saying, oh yes, I pressed a button because I thought of left hand opening or closing, there's still actually a world of difference between actually pressing that button and how quick and reliable that might be versus decoding algorithm that has to run and take a certain amount of data to actually be sure that you did this specific feature and selected that. And so as those get better and they start to merge together, I do think it's this really nice open-ended opportunity for people to think about how do you design the human computer interface and interaction space to make it more intuitive to use and feel better to use. So like with the Narami game that I showed there, one of the big decision points and one of the big levers we have is that it's using motor imagery. It's using this imagined action to fill up a bar. And as you fill up that bar, we can actually change the rate of fill. We can change things like the rate of decay, and we can personalize that per person so that it feels better for one person to use than just saying this is what it is for everybody. And so it's changing essentially how that button and that button press would feel as a user on it. And as this goes forward and we see more and more individuals using this for things beyond rehabilitation or access technologies, I think it's really key and critical for us who are trying to build this from the ground up to be aware of how to build those things effectively so that these applications could be used not just by the young woman you see here, but by everybody, and that she could play on an even scale with other individuals. So I don't know if that answers your question right away. I got a bit sidetracked in my own mind. Um, but realistically, over the next 5, 10 years, as things continue to grow, I hope our approach to designing these to make them feel good to use also grows.
Awesome. No, that makes perfect sense. Yeah, thank you so much for sharing all those insights. Well, we have a couple more questions kind of scattered throughout here, but I think maybe just since we're right at time, sadly, it's probably best that we wrap up the session. And we're happy to connect people with Eli for those who are interested in learning more. And yes, so for everybody who joined us today, thank you so much. If you're interested in learning more about these projects, we'll send a follow up with Eli's links so you can reach him, as well as the BCI for Kids website. And if you're interested in learning more about our DSI systems and how they could potentially enable your BCI applications or projects, please feel free to reach out and connect with us at Wearable Sensing. We'd love to support your efforts. And yeah, that does it for our session today. So thanks again, Eli, for joining us. Everybody have a great rest of your week, and we'll see you next time for episode 3.
Sounds great. Thanks so much, everyone. Take care.